Hello students, today we will be discussing some important reactions of carboxylic acids, namely Hell-Bollard-Jelinski reaction, Schmidt reaction, conversion of carboxylic acids to acid chlorides, Fischer esterification, de Colvé reaction, and lastly the Hans-Dicker reaction. Now let us first discuss the Hell-Bollard-Jelinski reaction. Hell-Bollard-Jelinski reaction is the halogenation of carboxylic acids at the alpha carbon atom by treating red phosphorus and bromine with carboxylic acids at above 373 Kelvin. An example of HBJ reaction, that is Hell-Bollard-Jelinski reaction, is shown on the screen. You can refer the diagram given there. Here carboxylic acid reacts with red phosphorus and bromine in the presence of water to give alpha bromocarboxylic acids. In the first step, the oxygen attacks the phosphorus and bromide ion becomes a good leaving group. Then the bromide ion attacks the carbonyl carbon of the intermediate form. In the second step, the hydrogen bromide donates a proton to the carbonyl oxygen and resulting bromide ion captures the hydrogen which was in the alpha position. Thus, the keto-enol tautomerism is achieved. In the third step, the carbon-carbon double bond then attacks a bromine atom and thus the bromination of the enol at the alpha carbon occurs. The bromide ion also removes the hydrogen bonded to the oxygen atom and forms another hydrogen bromide molecule. In the fourth step, the acyl bromide is hydrolyzed to the carboxylic acid with the addition of water. The bromide ion is expelled when the reformation of the carbonyl group occurs. The resulting product is the alpha halogenated product. Hope you understand the mechanism thoroughly. You refer to the diagram given on the screen and go through the mechanism properly. Now, let us come to the next named reaction, that is Schmidt reaction of carboxylic acids. Schmidt reaction of carboxylic acids is a reaction between a carboxylic acids and hydrazoic acids in the presence of concentrated sulfuric acid to give primary amines. The example of the reaction is shown on the screen. Here in the mechanism, it begins with the formation of an acylium ion from the protonation of the carboxylic acid followed by the removal of water. This acylium ion is now reacted with hydrozoic acid leading to the formation of a protonated azidoketone. Now, the protonated azidoketone and the R group undergo a rearrangement reaction resulting in the migration of carbon-nitrogen bond and the removal of dinitrogen leading to the formation of a protonated isocyanate. Then, a carbamate is formed when water is introduced to attack the protonated isocyanate. The carbamate is now deprotonated. The subsequent removal of carbon dioxide yields the required amine. So, I hope you understand the mechanism. Now come to the next. Next is the formation of acid chlorides from the carboxylic acids using thionyl chloride. So the formula is written as SOCl2. Here carboxylic acids react with thionyl chloride to form acid chlorides. During the reaction, the hydroxyl group of the carboxylic acid is converted to chlorosulfide intermediate, making it a better leaving group. The chloride anion produced during the reaction acts as nucleophile. In the first step, the nucleophilic attack on thionyl chloride occurs and the intermediate chlorosulfide is formed by the removal of chloride anion as a leaving group in the second step. Next, in the third step, we observe the attack of the intermediate again by the chloride anion, which is followed by the removal of sulfur dioxide and chloride ion in the subsequent step. The last step involves the deprotonation of the product formed in the previous step, resulting in the formation of acid chloride with the release of hydrochloric acid as a byproduct. So this is one of the common method of the conversion of carboxylic acids to acid chloride using thionyl chloride. Hope you all understood the mechanism clearly. Now, let me explain you the next reaction called the Fischer esterification reaction. The Fischer esterification reaction is an organic reaction which is employed to convert carboxylic acids in the presence of excess alcohol and a strong acid catalyst to give an ester as the final product. The Fischer esterification mechanism must include the continuous removal of water from the system or the uses of a large excess of alcohol, since the overall reaction is reversible. This ester is formed along with water. The reaction is an example of a nucleophilic acyl substitution reaction. That means it is based on the nucleophilicity of the alcohol and electrophilicity of the carbonyl carbon. Now, let us discuss the mechanism. In the first step, the carbonyl oxygen is protonated by the acid catalyst, activating it towards a nucleophilic attack from the ethanol as shown in the figure. In the second step, we observe that the alcohol executes a nucleophilic attack on the carbonyl carbon. A lone pair of electrons from the oxygen atom of the alcohol forms a bond with the carbonyl carbon, breaking its pi bond with the other oxygen. The pi bond electrons move up to the oxygen and neutralize its positive charge. This results in the formation of the oxonium ion. In the third step, a proton transfer occurs from the oxonium ion to the hydroxyl group, that is OH group, giving rise to an activated complex. This can be divided into two further steps, where the alcohol first deprotonates the oxonium ion, giving a tetrahedral intermediate, after which the hydroxyl group accepts the proton from the alcohol. This step is shown clearly in the diagram. In the next step, the 1,2 elimination of water occurs, giving the protonated ester. A lone pair of oxygen forms a pi bond with the carbon, thereby expelling the water as shown in the screen. In the last step, the remaining positively charged oxygen is deprotonated, giving the required ester as a product. So these are the steps of the reaction mechanism for the formation of esters from the carboxylic acids. Now, come to the next reaction, which is known as the Kolbe reaction. It is also known as Kolbe-Schmidt reaction. So, the Kolbe-Schmidt reaction is a type of addition reaction. In this reaction, phenol is treated with sodium hydroxide and phenoxide ion is generated. The phenoxide ion generated is more reactive than phenol towards electrophilic aromatic substitution reaction. Hence, it undergoes electrophilic substitution reaction with carbon dioxide, which is a weak electrophile. Orthohydroxybenzoic acid, the common name is salicylic acid. It is formed as a primary product. This reaction is popularly known as Kolbe's reaction. The mechanism of Kolbe reaction proceeds through the nucleophilic addition of phenoxide to carbon dioxide, yielding the salicylate. The salicylate form further reacts with acid to form salicylic acid. It is a carboxylation reaction where sodium phenoxide is heated with carbon dioxide under a pressure of 100 atmospheres and a temperature of 125 degrees Celsius, and the resulting product is treated with sulfuric acid to yield salicylic acid, which is an aromatic hydroxy acid. Thus, the required aromatic hydroxy acid, salicylic acid, is produced via the Kolbe reaction. It can be observed that there is a nucleophilic addition of sodium phenoxide to carbon dioxide gas to form the salicylate in the mechanism. Now, come to the last reaction called the Hans-Dicker reaction. Hans-Dicker reaction is a chemical reaction that involves the silver salts of carboxylic acid reacting with halogens to form the unstable intermediate, which further undergoes decarboxylation thermally, leading to the formation of a final product known as alkyl halides. Hans-Dicker reaction mechanism involves the formation of the reactive intermediate, the occurrence of decarboxylation to form a diradical pair, and the recombination of reactant to form the desired product. The reaction starts by heating of silver carboxylate in carbon tetrachloride along with bromine. During this, the silver carboxylate is transformed into acyl hypobromite, which is mainly due to the presence of bromine. Then precipitation of the stable silver bromide takes place. Consequently, a radical chain reaction takes place involving homolysis of the weaker oxygen-bromine bond. This results in the formation of a bromine atom and a carboxyl radical. This carboxyl radical, the decarboxylates, resulting in the formation of diradical pair of a hydrocarbon radical or an alkyl radical, which then recombine to form the desired halide, which in this case is an alkyl bromide. That's all for today. Thank you so much.